Now let's look at the solution set for t of x equal to b. And it's going to mirror the same concept and solution set for ax equal to b. So we have first transformation t goes from a vector space v to v prime. Let's assume that. Then we know that the kernel of t is equal to t inverse, basically everything that maps to 0. So it's the t inverse of 0 prime, which is a subset of v. So not a subset of v prime, right? It's in v. So those are all the solutions to t of x equal to 0 prime. Okay, so that's what we're talking about. All right. Let's also let t of x equal to b, as we stated above. And that's true for a particular vector in V. Then the solution set of t of x equal to b is the set, and this should look familiar, it's the particular solution plus h, which is the homogeneous solution. Okay, but what we're going to say then is that h is in the kernel of t. So let's take a look at a diagram of that. Let's draw in our circles, just copy that. So it's the same size. So we go from v to v prime. So we have v to v prime, and then we have our transformation t. So just in general, we have v and v maps to v prime in v prime, so you have that type of mapping. Then you have a particular solution, p, mapping to, say, b, like that. All right, so that's like a vector 1, 2 mapping to 3, 5 or something like that. So then what you also have is all the homogeneous cases. So over here is the kernel of t. So this is where you have your 0 vector and all your h's. That's going to map to 0 prime. So those map like this. That's the concept. So we have then t of p plus h is equal to t of p plus t of h, because that's just a linear transformation, which then is equal to b, because that's what t of p is assumed to be, your particular solution, plus 0, which is equal to b. And that's exactly the format we would have had for a matrix. So if you put in the matrix form, it would be a of p plus h, just like that. So that's just what we had before. So you could actually just fill it in directly. You have the same exact form. All right, then let's look at this concept. We're going to get into the concept of one-to-one and onto. So to start that, let's look at the kernel. So when you're mapping all of these, if all of these elements map to 0, then if you map 0 back with an inverse, well, that's not a function, right? I mean, 0 prime is mapping back to all of these other elements. So then in that case, it wouldn't be T inverse, in other words, would not be a function, would not be a linear transformation either. So first it has to be a function for it to be a linear transformation. So if the kernel of T is equal to just the 0 vectors, in other words, just 0 maps to 0 prime and 0 prime maps to 0, then T of x equal to b has at most one solution. Has at most one solution. So that is going to describe the concept that T is one-to-one, which means that T of if T of V1 equals T of V2, that implies that V1 equals V2. So you don't have two different values, V1 and V2, mapping to the same thing. Or I'm sorry, it implies they're equal. So it's not like x squared. So if you have like x squared, which is not linear, by the way, but then you put in 2 and negative 2, it maps to the same value. But they're different. So for it to be one-to-one, they have to be the same. All right, and then we'll define in a second. We'll get into the concept of onto. So we're going to continue with this. We're going to define one-to-one, and we're going to define the concept of onto. Let's quickly, well, look.